Hello everyone, I'm Arash Pourhabibi, and in the next 20 minutes I'm going to present our recent paper called Optimus Prime, Accelerating Data Transformation in Servers, and this is the video I'm recording for ASPLOS 2020. Modern cloud applications are constructed as microservices. These fine-grained components are developed independently using various programming languages and tools and are typically connected via RPCs. Hence, to provide interoperability, RPCs rely on data transformation to convert data back and forth between microservices format. For example, in this figure, different colors represent different programming languages. It's been shown by cloud app providers like Google or Facebook that DT forms a significant fraction of spent CPU cycles, something between 5 to 15%. It's also almost 2 orders of magnitude slower than the network's line rate, making it a performance bottleneck. Hence, in order to maintain performance scaling of cloud applications, we need to be able to do DT at a much faster rate. DT occurs for every network message between microservices, even between those written in the same programming language, as data has to be flattened on one side and unflattened on the other side. The problem is, while DT is an inherently parallel task, the software implementation is not. As shown in this figure, we have 2 microservices on 2 sides, and microservice 1 wants to send a message to microservice 2, which is written in a different programming language. While the object layout exposes the field-level parallelism inherently available in this task, the software implementation running on top of the CPU performs these tasks sequentially. The granularity of each transformation is too big for the CPU's ILP window and yet too small to amortize the synchronization cost for thread-level parallelism, hence forcing the sequential execution of this parallel task. So the insight here is DT is an inherently parallel task, and this parallelism should be explicitly exposed to hardware. In this paper, we introduced transformation schema, an abstraction to express DT tasks. It's based on the object layout and exposes the field-level parallelism to hardware. We also introduce Optimus Prime, a DT Accelerator that parses this schema and performs data transformation at network's line rate. Optimus Prime achieves 60 times higher throughput and near 2,000 times better performance per watt compared to commodity CPU cores. As shown in this figure, with Optimus Prime, fields are now processed in parallel, which is enabled by the use of our transformation schema. So that was my introduction. I briefly explained our motivation for this work, our insight, and our contributions. Now I'll give a more detailed explanation of what DT is and why it's slow and why we need to accelerate it. Next, I'll talk about our hardware-software co-design for rapid and flexible data transformation, followed by evaluation highlights. And I'll give a brief summary in the end. So just to recap our motivation, we know that cloud applications rely on a data transformation layer to convert data back and forth between formats. For example, Google's Protobuf or Apache Threads. As data center networking technologies continue to scale both in software and hardware, wire time and transport time have shrunk dramatically. The DT layer hasn't changed that much and is orders of magnitude behind in terms of performance. As you can see, as the new networking technologies continue to scale, DT will soon account for a considerable fraction of the end-to-end latency, making it the next logical step to revisit to keep up the performance. This gets exacerbated as processing times of microservices are shrinking to microsecond scale. To better understand what happens internally, here we'll look at the serialization example in Protobuf. To serialize an object, each field has to be transformed individually. It has to be read first, then transformed, and written to an output buffer. Here we have the same person object we had before. It has 3 fields, an integer, a string, a phone object, which is a submessage and has its own structure, and we will see how this message gets serialized. So first, the ID has to be transformed. Almost all of these DT frameworks have this notion of keys and values. Each field gets translated into a key, also known as a tag, and a value, where the key is used later at the serialization time to identify that field. So Protobuf has its own way of creating the tag and is based on the field's type and its ID number. Here, because it's an integer field and the ID number is 1, the tag will be 08 in hexadecimal. Next, the actual value of the field has to be encoded. Protobuf uses variable length integer encoding, or varint for short, to represent integers. This means while this field is a 64-bit integer, Protobuf only uses the number of bits required to represent the number and not all the 64 bits. The number is first broken into 7-bit chunks and reordered, and the continuation bit is used to signal there is still more bytes to follow. When the continuation bit is set to 0, it means it's the last byte of this number. What I didn't tell you before is that tags are also represented as varints, so this is a very common type of transformation in Protobuf and even in Apache Thrift. Now it's the second field's turn. We will again have the tag. In this case, it's going to be 12. And we will have the size of the string after the tag and before the characters are written, which is 8. The size is also a var_int, and the characters are each represented by a byte. Finally, as phone itself is a submessage, Protobuf will recursively serialize this phone object, but we won't get into that in this example. So as shown before and as you saw here, what we saw was actually what happens internally in order to serialize an object in Protobuf, and more importantly, we saw this was done sequentially, while it could have been done in parallel because we have the field level parallelism exposed by the object layout. While we only talk about serialization here, deserialization is somewhat similar process which happens in reverse. In principle, each field could be independently transformed if the hardware was aware of field's type and memory location. So as we saw earlier, while DT is an inherently parallel task, the software implementation is not. This is mainly due to the use of ISA as an abstraction to represent the underlying operations. The software implementation relies on implicit instruction level rather than explicit field level parallelism. The task granularity is too big for CPU's ILP window, and it cannot find enough parallelism. In this figure, we have more or less the pseudocode for the var_int encoding we saw earlier, and expressing such complex operations, as you can see in CPU's ISAs, entails high instruction count per field, which, when added to the instructions required to read the data, it all adds up to hundreds of instructions per field, or between 20 to 30 instructions per output byte. Moreover, as such operations rely on the value of each byte, they have a data-dependent control flow, which limits attainable parallelism. Finally, we cannot rely on thread-level parallelism, as these tasks are variable-sized and too fine-grained to amortize the synchronization costs. So neither the CPU's ISA nor software threads are the right form of expressing the inherent field-level parallelism in DT tasks. We need to co-design hardware and software together around an abstraction that explicitly expresses parallelism. And we need specialized hardware units that parse this abstraction and do rapid data transformation. So now that we know what data transformation is and why it's slow, I'll talk about our hardware-software co-design for rapid and flexible data transformation. Particularly, I'll try to answer these 3 questions. What interfaces should the accelerator have with the software and the server system? What should the accelerator, where should the accelerator reside in the server? And what components should be the building blocks of this accelerator? Transformation schema is our key enabler. It is the abstraction we created to expose the field-level parallelism to hardware. It's based on the object layout and contains a collection of type address pairs each representing a field of the object, which enables hardware to operate on each field independently. It also makes the accelerator using it framework agnostic. The framework just needs to create this schema, for example, using the setter methods, and pass it to hardware. So here we have the same person object. As you can see, the schema points, each field of the schema points to each field of the object. And if the field is a message itself, it points to the schema of that object. Parsing this schema, the accelerator will know what it has to do and where to get the data from. So the schema unlocks the field level parallelism and makes the accelerator framework agnostic. Now that we have the schema, we need to talk about the design of the DT Accelerator or DTA. We start with its location and interface. Because of the microsecond granularity of data transformation tasks, the accelerator needs to have a fast interface. We use polling and MMIO to minimize the invocation latency and believe the DTA should be integrated on chip to minimize the time it takes to fetch the data, rather than having it connected through PCIe, for example, as it introduces a microsecond scale delay for every pointer chasing. Regarding the location, we now have two choices for the on-chip integration. Private per-core DTAs allow sharing the cores L1 and TLB, but they are inefficient as they require replication and they suffer from low utilization. Shared DTA, however, provides higher silicon provisioning efficiency and utilization, but it requires a small scratchpad and TLB to access memory. We believe the DTA should be a shared component due to the fact that the silicon costs of private DTAs quickly add up with increasing core counts. Finally, to answer our last question, we need to identify what components the DTA should have. The DTA needs a component for communicating with the cores and keeping track of the requests. It needs a component for parsing the schema we just talked about, and we need a specialized component for the actual transformation, which can do those like such complex transformations in a few cycles. As this component can do transformations in a few cycles, then the memory access cost will limit the performance and will be the bottleneck. So we need to use the decoupled access execute model to overlap memory accesses with transformations, which means separate components for reading and writing from and to memory. So here is our implemented DT Accelerator, Optimus Prime, or OP for short. It has a dispatcher, and as you can see in the figure, this dispatcher is in charge of the communication with the cores and keeps track of the requests. It can have one or more transformation pipelines, each including a reader, a converter, and a writer. The reader of the transformation pipeline parses the schema, fetches fields, and passes them to the converter. Then the converter is the one that performs the actual data transformation. The converter is a 4-stage pipeline and has a small instruction memory, which makes it programmable and allows compatibility with future data formats. The writer gets the transformed fields from the converter and writes them to the output buffer, for instance, in case of the serialization. In addition to these, OP has a block buffer which acts as a scratchpad, and its role is to communicate with the on-chip memory hierarchy and translates the virtual addresses. OP also uses prefetching and time sharing the units to hide memory latency. Okay, so now I'll talk about our evaluation highlights, which is focused on OP's ability to perform line rate transformation. Here's our evaluation methodology. We use our cycle-accurate full system simulation infrastructure Flexus. We model a tiled 16-core chip with a mesh NOC and assume OP is attached to a node in the mesh. We run serialization and deserialization macro benchmarks based on Google's Protobuf using 3 message classes, flat, mix, and nested. In the flat messages, all fields are in the first level of the message, while in the nested, all fields of the first level are actually sub-messages, and all the actual fields that contain real data are at the second level. And mix represents something in between the two, which includes integer string fields both at the first level and also at the second level. For area and power, we synthesized our implementation using Synopsys compiler with TSMC 28 nanometer technology at 2 gigahertz and use Cacti for area and power of block buffer and the TLB. In the end, OP11, the OP configuration with one transformation pipeline and without time sharing, consumed just 0.12 square millimeters and draws 58 milliwatts of power. Here we show the throughput achieved by CPU and Optimus Prime for the 3 message classes when performing Protobuf serialization and deserialization tasks. OP base is the design without prefetching or pipelining enabled, and OP11 is the design with one pipeline and the degree of time sharing of 1, which means the time sharing is not enabled. As shown in the figure, for the flat message, OP base case performs serialization around 5 times faster than CPU. This benefit comes mostly from the converters performing the transformation in a few cycles. However, its performance is actually limited as it spends most of its time waiting for data to arrive. But when pipelining and prefetching are enabled, we see another 3 to 5x improvement, which adds up to around 20 times higher throughput with just a single transformation pipeline. This is mainly due to the schema, which exposes these addresses to hardware, enabling us to cut the average read latency by more than 3x. In case of nested, we see the worst case throughput, which is expected as it's the worst case scenario. It involves sequential pointer chasings to get to the data, and our prefetcher only prefetches one level at a time. The mixed messages fall between the other two cases as they share the characteristics of both flat and nested. Deserialization also exhibits the same trend, but a bit higher throughput because the already serialized input data comes from a contiguous buffer, thus enjoying high spatial locality. In case of the nested messages for deserialization, again, the degree of dependent accesses to the schema grows and limits the throughput. Even though a single pipeline attains up to 20 times higher serialization throughput, there is still headroom to achieve the target NIC bandwidth. We scale up OP with more pipelines, and here we show the serialization throughput achieved by Optimus Prime with more pipelines. Scaling up OP with more pipeline enables line rate transformation until the NOC bandwidth is saturated. That's where all these lines start to plateau. So while with 2 pipelines, OP achieves the line rate transformation for flat messages well above the line rate transformation for flat messages, it needs 4 pipelines for nested messages. And the line for nested messages, the yellow line plateaus at a lower rate because these messages are actually the least read efficient type of messages. For nested messages, for every output byte, OP has to read 4.25 bytes, while this read-write ratio is 2.6 for the flat messages. That's why the line for flat messages plateaus at a much higher throughput. Now let's talk about OP's area and power efficiency and compare them against CPU. OP with 1 pipeline and no time sharing takes less than 5% of the area of an A57 ARM core and delivers more than 600 times higher performance per watt. The OP design with 12 pipelines and no time sharing costs around 3.5 times of the design with 1 pipeline in terms of area, and it is a bit less efficient in terms of power as performance does not increase exactly linearly. When enabling time sharing, the OP design with 3 pipelines and degree of time sharing of 4 achieves the same performance of the previous case with 12 pipelines at a much smaller area and power consumption. It only takes 7% of an ARM core's area, but delivers around 2000x higher performance per watt. compared to the CPU core, and more than 3 times higher than the previous design with no time sharing. So to summarize, we need to do hardware-software co-design for rapid data transformation, as DT forms a significant fraction of the spent cycles and is becoming a bottleneck. We showed while data transformation is an inherently parallel task, the software implementation is not. The CPU's ISA is the wrong abstraction to express these tasks, and DT is actually ill-suited for CPUs. We introduced Optimus Prime, a programmable DT accelerator that uses transformation schema, a novel abstraction to express data transformation tasks based on the object layout. OP delivers 60 times higher throughput compared to software at a tiny fraction of the CPU's silicon overhead and power, and it removes DT from the critical path by achieving the line rate transformation. Thanks for your attention, and thank you for watching this video till the end. For more information about this work, please check out our paper. It includes more details on our design. And as we only had time to cover the highlights of our evaluation, please go and do check our paper for more information on, for instance, including OP's effect on microservices latency. Visit our website for more information on this work and other projects, and thanks again.